For this video, you need to be in task 5. In task 5 reads, use your Slinky spring model and other materials to develop a model that quantitatively demonstrates the relationship between amplitude and energy in a wave. So task 5, we have been talking about if energy goes up, amplitude goes up, and if amplitude goes down, energy goes down, that there's this direct relationship, but we have not put numbers to it. Next to quantitatively, please write numbers. We need numbers. We've got to prove what happens. How much does energy go up when amplitude goes up? Or how much does energy go down when amplitude goes down? So in order to do that, we've got some materials here. You can see I've got a cup, a Slinky spring, and if you can see it, there's a line, which is the center line that they're both kind of sitting on right now. And then there's a vertical line we're going to use. So we made these procedures, and I'm going to let you pause the video when I hold up this picture. And on your page, these are the procedures we use. Please write these down. We made this grid that's already on here. We marked every 10 centimeters from 0 to, we went up more than 30. We positioned the Slinky spring along the center line, positioned a half-liter container so that it comes in contact with that with the transverse wave made by the Slinky. And position the half-liter container then make a mark on the chart paper to indicate the starting position. We actually are just using the starting line here. When one person holding each end of the Slinky, model a wave with amplitude of 10 centimeters. Once the wave is collided with the cup, measure how far the cup has moved. That would measure our energy. Repeat 2 more times, so we get 3 trials with 10 centimeters. Then we went up to 20 centimeters, did it 3 times, and then we went up to 30 centimeters. So let me show you what these steps mean. So I want to make a 10 centimeter wave, amplitude. So here on my grid is 10 centimeters. Down here is my resting position. So just to practice, I'm going to make a wave that just goes up to 10 centimeters. Okay? Now, I practiced, I kind of know what that's going to look like. So now I'm going to take my cup and I'm going to put it on the center line and put my spring right there touching it, and I'm going to go up 10. Okay? Well, to make a 10 centimeter 10 centimeter wave, I'm going to count. This should be 12, and now it's almost 14. So it ended up 14, okay? And then I would do that 2 more times. So I'm going to let you get your data from your group for that, but then we would have gone up to 20. So we put our cup on the center line. Then, of course, before that we would want to practice going up to 20, and we'd see it takes more energy. So I'm going to put my cup back up there, and I make a 20 and it goes way up there. Okay, I would do that 2 more times and get that data. Now I'm going to go up to 30. So now I need a lot of energy to flick that up there. So I'm going to put my cup down. And again, remember, I've done 3 trials for each of these and recorded it. And I'm going to go really high and measure that. And if you measured that all the way up, it almost gets to 100 centimeters all the way up there. Okay? So I need you to get that data from your group, but I'm going to show you kind of what the data table would look like, and then I'm going to show you what the perfect world would have given you. So, in task 5, at the bottom of your paper, you need to have a data table that looks like this. Okay? So make sure you have that, and I need you to get that data from your group. So pause the video if you need to get that. Okay, and then I'm going to show you what would happen in a perfect world. Please write this down. In a perfect world, you would have gotten on average 12, 48, and 108, because after the 3 trials, we always take the average. So if you see, and I'm going to give you a little hint, pause the video here and see if you can figure out the relationship, okay? And I'm going to show you on this paper how it works. So, if you double the amplitude, 10 times 2, you get 20. If you, so let me show you. To get on the amplitude, you go 10 times 2, you get 20, you double it. But over here, sorry about that, to get to 48, it's 12 times 4. So what's going on? Instead of doubling, when you double amplitude, it doesn't double energy, it actually makes it go up by 4. So look at the next line, see if you can figure it out. Okay, so again, this is what it would look like mathematically on the last line, 12 or 10 times 3. So if you triple, you actually go up on the right 9 times, 12 times 9. So what's going on? When you double amplitude, you're actually not going up by 2, you're going up by 4. And when you triple amplitude, you go up not by 3, you go up by 9. Well, what's really happening is every time you proportionally go up with amplitude, so say you go up 3 or you go up 2, you're actually squaring the energy, because 2 times 2 is 4 and 3 times 3 is 9. So every time you go up so many times in amplitude, you square that energy. It takes so much energy to just move your amplitude up, either double or triple, moving it up so many times. So here's kind of what the explanation they have at the bottom. You don't necessarily have to know the math, you just have to know that it does not look like a proportional graph. It does not look like what you learned probably in math this year. When you graph this, it's not going to look like this, because when you double one side, it doesn't double the other. That's not right. Okay, so I would cross that out. What the graph is now going to look like is this. Okay, that's an exponential growth. Okay, so on your paper, I want you to write exponential growth. So every time amplitude goes up by a multiple, the other side goes up by that exponent of that multiple. Okay, so it takes a lot of energy to get your amplitude increased. That's what they're trying to get you at.